Record. I'll hit this too. Okay, welcome to 2023 Spring Seminar Series for the Iowa Nutrient Research Center. Thanks for attending here and continuing on with talking about highlights from a decade of research and impacts with INRC. And this month, we are going to be focusing on saturated buffers with Dr. Tom Isenhart and Dr. Chris Rehmann. Dr. Isenhart from the Department of Natural Resource Ecology and Management, and Dr. Rehmann from Civil Construction and Environmental Engineering here at Iowa State University. And they're going to be talking about saturated buffers. And I just want to highlight that the saturated buffers received recently NLA, National Lab for Ag and the Environment, where retired colleague Dan Janes worked. The saturated buffer concept received the 2023 Federal Laboratory Consortium for Technology Transfer Award. So a great award for NLA there. With that, I'm going to turn it over to Tom for his part of the presentation, and then we'll transition to Chris. We'll see if I can share my screen. Yes, Tom. What's that? Just use it. Yeah, just use the mouse. So hopefully, Malcolm and Kay, can you see the? Okay, all right.
We're in business. Thanks, Matt. And thanks for the opportunity to be able to present the work on saturated buffers that we've been doing throughout that whole decade of the Iowa Nutrient Research Center. Again, thanks for the opportunity. And like most times when I present, I'm presenting mostly the work of others. And so I have the list of all of them there rather than go through them because you can see it's a rather long list. I'll just acknowledge all the important contributions there. So my goals today are several. One is to sort of give the history of saturated buffers and present sort of the status of the science, and then hand it off to my colleague Chris Rehmann, who's going to dig in deeper on a couple of the aspects. But I also want to take the opportunity to sort of use it as a case study for how we go from an idea about a conservation practice all the way through something that's widespread implementation, which has probably been as much of a learning experience in saturated buffers as the science itself. So the history goes all the way back to our work down in Bear Creek. So my colleagues Dick Schultz and Joe Coletti started working with Ron Risdall and other landowners up in Bear Creek, north of Roland, Iowa, to establish what was then a novel practice of riparian buffers and filter strips. And then they were more widespread implementation after the change in the Conservation Reserve Program in 1996, and now we started to take them for granted. So we've been working there to look at how buffer performance and how they act to provide those ecosystem services. One of the things that we've been looking at is how well does converting row crops right up to the field edge to perennial vegetation, how does that change nitrate removal within that shallow groundwater? We did that by establishing a series of wells from the field edge across that riparian buffer towards the stream in transects at 3 different locations, and then monitored that for now over 20 years. And what we saw has been best summarized by Tyler Groh, PhD student who's now in the faculty at Penn State University, that summarized those 20 years of data. And we look at it here, and it has relative nitrate removal across that buffer, and looked at it over time from a crop field to recently planted, a younger buffer, and a more mature buffer. And you see that line. We did have removal early on, but removal performance increased over time. Okay, the importance of that riparian vegetation providing carbon, labile carbon, changing soil structure. So his research showed that all 3 buffers reduced nitrate concentrations establishment. Previous land management was important. There was residual effect there, and that riparian vegetation established positively affects nitrate removal. Well, so there we were. But the issue we had in Bear Creek is that from north of that landowner, from Ron Risdall's up to the headwaters, there were about 50 of these artificial subsurface drains, these tile outlets. And so these tile outlets were short-circuiting that buffer, providing that direct conduit from the nitrate and short-circuiting the buffer performance. So what were some of the options? What could we do about that? Well, enter these two cast of characters. On the left-hand side is Dr. Dan Janes, recently retired from USDA ARS National Lab for Ag and Environment. On the right is Ken Hykins, who's also recently retired from USDA and a long-term technician there. All right, so I'm not going to provide any comment with respect to the representativeness of these two photos, with Dan on the left-hand side with his foot up on the water control structure, mugging for the camera, as opposed to Kent, who's down in the hole working with the contractors. But Dan, and as I'm fond of saying, and Dan and I were in a meeting in Kansas City, and he came up to me and suggested this idea. And what was this idea? This idea was here, is that we take, you see that tile drain, and it's moving from that crop field across that filter strip to the stream, providing that direct outlet for nitrate, and said, hey, how about we take that and we put in a control structure, and then we run tile drainage, we run perforated tile along the buffer, put those gates in there, put some hydraulic head on it, and thereby force that water out into that distribution line, back into that riparian soils, and utilize that capacity that we knew was there for removing nitrate. Importantly, then in this design, it has those gates that you see in there, and that any excess that can't be taken down that distribution line and infiltrated into the riparian soils just bypasses that, re-enters that tile, and then enters that stream. So we're not removing any drainage rights for the upstream landowners. So that was his idea. And at the time, there were a couple of other options. Bioreactors were already being implemented. Nutrient removal wetlands, which was more of a larger watershed, larger tile area, but this was a novel concept at the time. So we went up, and I worked with some of our long-term cooperating landowners and operators, and we surveyed a few sites, and we settled on this one, which was known now as Bear Creek 1. So Kent Hykins and Carl Peterson trenched this one in, and so you can see the box on our Bear Creek 1, and then that trench, that tile line that's going back upstream in this case, where we put that distribution line upstream and downstream. So our first site was put in fall of 2010, with monitoring starting in 2011. So the design, so we could get some estimate performance effectiveness of these buffers, is here. You can see the field tile coming from the bottom in the lower right. The pink is that 3-chamber control box, and the distribution line is 900 feet upstream and a little over 100 feet going downstream. And then we put a series of observation wells. In this case, we have 4 transects of wells, 3 wells in each transect, and then we monitor those for head, and then nitrate concentration, both at the box and then in those wells. And so then performance effectiveness is then assessed by the concentration in the box versus the concentration in the wells times the mass of water that's been diverted. Okay. Well, what we find, to summarize a lot of data in just one quick slide, they found that this site worked, and this site worked very, very well. So here's a summary of about 6 years of data with nitrate concentration on that y-axis. And so that's a long-term average nitrate concentration within the tile in the first bar, and then that series of wells nearest the tile, and then 3.7 meters, 5.6 meters, and 11.6 meters heading out towards the stream, and 18 meters in this case. And you can see that line going down, that arrow going down. So nitrate concentration was removed, and removed dramatically. That's one of the things that we've seen, is that in virtually every site, we do see significant nitrate removal as that water moves across that riparian zone in those high carbon riparian soils. They differ a little bit based on factors that we're trying to assess, but there's a large capacity for removing nitrate once we get the water in there. Oftentimes, most of the time, that is not the limiting factor in overall performance effectiveness. So then, based on that, we established a second site with USDA National Lab for Ag and Environment, and then with the Water Quality Initiative now up and running in 2013, and with support from the Iowa Nutrient Research Center, we've established now a network that increased to about 20 different sites across the state that were fully monitored for nitrate concentration and flow. So we can get performance effectiveness on all 20 of these. We've cut back on a few of them over the last year. But this allowed us to look at the performance across a range of conditions. And it also, I think importantly, provided some demonstration sites for those local water quality watershed coordinators to demonstrate the practice within their own watershed. So one of the other things then is, so the backstory of all this is, so now we have a practice that looks like it works, and we want to implement it broadly. Well, to be able to do that and access the cost shares, we have to come up with a conservation practice standard. So we worked with the USDA Natural Resource Conservation Service to establish an interim conservation practice standard, and then several iterations. So the first one, final one, was in 2016, modified in 18, and then there's a newer one out. So in there, we have to have some criteria by which to establish that. And some of that was based on the knowledge and the information we've already collected. Some of it, frankly, was our best assumptions. So we have to say, all right, if we're going to invest those public dollars, what's the minimum performance effectiveness that, is worth it to get that out? And one of those was this design flow capacity. We said the minimum design flow in the saturated buffer should be at least 15% of the maximum capacity of the drainage system. Said, all right, if you look at that drain that's feeding that saturated buffer, we should be able to capture at least 15% of that flow in order to make it an efficient system. We subsequently brought that back to 5%, and then the newer one doesn't even have a percentage in it, although the design spreadsheet still has a percent in it. Now it's as much as possible. But that was one of them that we looked at, and that's going to be important. We'll come back to that. Minimum width of the vegetated buffer should be at least 30 feet to maximize that denitrification or nitrate loss. But there was concern that by elevating that water table in the riparian zone, we might be increasing stream bank instability. So we should avoid placing the distribution pipe along channels in size deeper than 8 feet. We need the carbon to fuel that denitrification and that nitrate loss. So a minimum of 0.75% organic matter, 1.2% or percent organic carbon, 0.75% organic carbon, 1.2% organic matter in the top 2.5 feet of soil. And then some other things like consider adding an envelope around a drain to improve exit flow, or to add other water control structures where the topography needed to assure flow uniformity. So then what that did is that also then provided things for us to look at. Were we right? Can it be improved? Okay, and so some of this drove the science. Some of these questions drove the science. So one of the things that I want to focus on for just a minute here is that nitrate removal capacity and that percent. So here you see two sites on the bottom, our Bear Creek 1 on the lower left there, and our Bear Creek 2, we'll call it, right upstream, just across the fence. So same soils, same farming practices, because it's the same landowner, same operator. So you see BC1, it's BC2 in the top left there. So they differ in drainage area. BC1 has a much smaller drainage area, at least initially, a lot smaller drainage area than BC2, which is 4 times the drainage area. Well, how about the pipe that we can get in there, that pipe length? Notice that in BC1, we could go about 1,100 feet, 1,100 meters. We could go quite a distance. But the bottom one, we could only go 550. Okay, so we were limited by, if you look at that lower right picture, we were limited by that fence line. All right, number of site years of data. So then after we look at performance over time, how do we measure effectiveness? The most common way to measure effectiveness is what's the percent of nitrate we removed on these systems? How much did we remove? Long-term average there highlighted for Bear Creek 1, we removed 42%. All right, Bear Creek 2, we only removed 19%. Okay, so if you just looked at it percent alone, we would say, hey, let's use the Bear Creek 1 is the more efficient buffer. And if we were limited by resources, we would choose Bear Creek 1 over Bear Creek 2. But an important thing to remember, like I mentioned before, is that once we get the water into that riparian zone, we see almost full nitrate removal. These systems are limited by how much is bypassed. What's the capacity of that drainage line to accept that water? So most of that 42% and 19%, that really means the rest of that water was bypassed. We didn't have the capacity within that drainage system. If you look then at 903 removal per drainage area, it's similar. It's telling the same story. But how about if we look at total NO3 removal, mass removal, and these are annual removal numbers, and compare it that way? The story couldn't be any more different. If we look at that, then we see 82 kilograms of N removed by Bear Creek 1 and about 2.2 times of that removed by Bear Creek 2. Okay, why? Because we're putting more water into Bear Creek 2. And so we have, and once it gets into that soil, we're removing about 100% of that nitrate. But the key is that we're putting more water in there. So we need to be careful about comparing percentages versus total kilograms of N removed. So our lessons are total N removed is controlled by that drainage area, how much water we're putting in there, and what's our length of buffer pipe. And we need to, and the percent of total N load removed is probably not the best indicator. Is probably not the best indicator of buffer performance. Okay, so then we did some other basic science as well, and we leveraged the resources put in by the Iowa Nutrient Research Center with some USDA AFRI funds and other funds, and now USDA NRCS Conservation Innovation Grant funds to look at some of the basic biogeochemistry. So here in the left-hand picture, that's two of the PhD students, Dr. Morgan Davis, now of Penn State, University of Missouri, Dr. Tyler Groh, again of Penn State. And so summarizing all of Tyler's work here, all his dissertation in one sentence, Tyler went out and collected innumerable cores within these buffers and sectioned them and look at denitrification through that acetylene inhibition method, and said that, hey, look, we look at those estimates, although they're highly variable, both the cumulative maximum and 90% confidence interval denitrification rates accounted for all of the nitrate removal, indicating that denitrification can be the dominant nitrate removal mechanism. So that's picture there on the left is sort of, I'll be honest, is a proud major professor picture there. That's the two of them at the Tri-Societies meeting, where this paper that Morgan and Tyler co-authored won the 2021 JEQ Outstanding Paper Award, and they're mugging with the paper in the background at the meeting. One of the things that that Morgan then looked at was, are we trading an a water quality problem for an air quality problem? Is that, are we getting indirect incomplete denitrification and increasing nitrous oxide removal or nitrous oxide production? Long story short, okay, while we did see some increases in surface emissions and increases in dissolved emissions of nitrous oxide, when you do the total mass balance and incorporate the indirect emissions, there's no difference in total nitrous oxide production between the saturated buffer and the traditional buffer. And importantly, they are both well below that we see within the crop field in the agricultural field immediately adjacent. So then really quickly, where are we going with this? We're looking at some innovative designs. One of the things that was in the conservation practice standard is consider putting a gravel envelope out there to increase the amount of water that we can infiltrate into the soil. So we have a site on one of the ISU farms, Boyd Farms, where we have a couple of years of data for this that we're looking at. Other ones we're looking at is dual distribution lines is suggested. And so we have a site on one of the ISU farms where we have dual distribution lines and a couple of years of data where we're going to be looking at, does that increase, how much does that increase that infiltration and nitrate removal? We're also looking at ones where we have topography where going downstream, the tile is getting too close to the surface. And so we put in a step down chamber in there where you can see that two chamber control box there in the middle. Okay, and then currently with a new Iowa Nutrient Research Center grant, we're looking at this concept of, can we extend this to other landscape positions? And one of those is a saturated waterway. And this is where a landowner came up with this idea in the left-hand picture, where you're using that waterway and that vegetation in that waterway as a saturated buffer. And another one where we're looking at is, can we intercept a tile and run that tile with a distribution line into a prairie strip and make it a saturated prairie strip? And then the last thing we're looking at is, we've avoided most areas where it's been flat enough that we've been concerned about backing water up seasonally within a landowner's field that's draining into that saturated buffer. Well, AgriDrain Systems now has these smart drainage systems out where we can use an app and we can control those automated structures from here. And so one of our PhD students, Gabe Johnson, is looking at these controlled drainage systems out there. And that's in cooperation with Chris Hay as well from Iowa Soybean Association. So with that, here's our lessons learned. We need to think about mass removal, not percent. We're not trading a water quality for an air quality problem. Denitrification is the main loss process. Perennial vegetation is important. So another study that I haven't mentioned is that Matthew Ford and Stephen Hall are looking at total soil respiration and carbon isotopes. And it looks like that not just total carbon, but the lability of that carbon is important in driving this denitrification process within these saturated buffers, and that improves over age. So then lastly, I'll say a couple of unanswered questions. Is 30 feet wide sufficient for nitrate removal? And do saturated buffers decrease stream bank stability? With that, you're going to have to stay tuned. And I'm going to yield to my colleague, Chris Rehmann, who's going to answer some of those questions.
If we transition, I'll get Chris's slide. If somebody has a quick question for Tom, we could ask it. I said that online too. Folks can either they want to unmute quick for one quick question or type it in the chat box as we get Chris's loaded up. Otherwise, there should be time at the end. Oh, okay, that's what I wanted. There we go. Okay. Can you guys see that online? Okay, I'll guess no question right now. We'll turn it over to
rolling. All right, I'll continue the discussion by talking about some attempts to improve the design of saturated buffers. And as Tom said, this is primarily the work of others, and the others in this case are two students, Andrea McEachran and Lulu Dickey. We acknowledge funding from the Nutrient Research Center, and I'll also talk about some work supported by the NRCS. Tom showed code 604. I want to just re-highlight a few things. There's the minimum width of 30 feet. Tom also said you have to keep the water up high in the soil profile to take advantage of the organic carbon. And so that the maximum distance of the water table from the ground at the control structure is a foot. And Tom also mentioned that putting water through the if the bank height is more than 8 feet, you should go into a geotechnical or geological investigation, which increases time and complication and money. So if you're designing a site, then you would use code 604. I'm showing it here schematically. You can see the tile going to the stream, the blue there. And so check the bank height less than 8 feet, then you could set the control structure a width LX of 30 feet or more. You would put the distribution pipe such that the water table, this blue line, is within a foot of the ground surface. Flow and a homogeneous unconfined aquifer. That's this equation down here. And I've written it not in terms of Ly, the length, which you're trying to calculate, but in terms of the flow, because I wanted to emphasize that everything else being constant, the flow decreases as you increase the width, Lx. So for the same difference in water levels, when you increase the width, you're getting less of a gradient, less driving force to get that flow through the buffer. And so here's the outline of my piece. We'll ask, as Tom said, is this an appropriate width of 30 feet? Is the flow 1D and steady? We know it's not steady, but it is one-dimensional. Is that a reasonable approximation? And then in terms of the slope stability, is there anything else that would be important? So first, the buffer width. This mostly comes from this paper here. And Tom already talked about this. The nitrate concentrations, these are at BC1. So I won't take a lot of time, but you can see, so I have concentration versus time for 2 years. And at the control structure, the values are above 10 milligrams per liter it steps down just as he showed. And for this data set here, 19 meters away from the control structure and the distribution pipe, the concentrations were below the detection limit. So these were 0. So as he said, these do a very good job of removing nitrate. All right, but this was before the stream. The wells weren't right at the stream. So then Andrea and I said, well, we can make the buffer narrower, right? We're taking up land that we don't really need to in this case. So we looked in more detail at the effectiveness of the buffer, which we defined as 1 minus the mass flux out divided by the mass flux in. And Tom said this, here's the math if you want, if you're into the math, which I am. So there's the mass flux in, which depends on the concentration and the flow from the field. And then there's the mass flux out, which has 2 parts. There's what goes into the buffer at a flow Q. Concentration C out would be what's right at the end of the soil, just as it's going into the stream. But there's also the overflow, just as he said, we don't want the field backing up. So this control structure has a mechanism to let high flows partially bypass. And so those are the 2 parts of the mass flux out. And so the effectiveness involves this flow ratio and concentration ratio. And so what you would want to do is reduce C out, because you're trying to get to 100% or this effectiveness of 1, or maximize, and maximize Q. In fact, as Tom said, these buffers, the concentration going out is effectively 0. So if that's 0, really the effectiveness is totally dependent on how much of the flow you can get into the buffer. So that's a key point. So how do you reduce C out? Easy, right? You increase the width, and so you give it more travel time. How do you maximize Q? You decrease the width. So you have this trade-off or tug of war or optimization problem or Goldilocks situation, whatever you want to call it. Here's the effectiveness as a function of the buffer width divided by the optimal width. So for widths smaller than optimal, you don't have enough time to remove the nitrate. Widths greater than optimal, you're not getting enough flow. So another way of saying that is you want that water just as it's reaching the stream to be giving up its last bit of nitrate. So you want to balance the time for travel and removal. So travel time is the width divided by the average linear velocity. This is a one-dimensional approximation. It involves the effective porosity and some relations from CE473, 573, Monday, Wednesday, Friday at 11, and the fall. Is that allowed, this shameless self-promotion? Yeah, okay. And then we're assuming here first order removal at a coefficient lambda 1 over time. So you balance these times. This do? Or let's calculate it. Let's see for these 6 sites. So here's buffer width, the blue is the current width, the orange is optimal, the dashed line is the code 604 minimum width of 30 feet or 9.1 meters. And in this analysis, for all 6 sites, all 6 sites are wider than optimal. And for 2 of the sites, the optimal width is smaller than the code 604 minimum. So this approach puts a more systematic way of estimating the width of the buffer. It gives another basis for estimating the width. Now you see large error bars. That's because use the fear of public humiliation to advance this analysis. So in the previous analysis, effectively, we were assuming that the head difference was constant. So that is effectively saying that the ground is flat. And Tom was just saying, you don't want it to be flat because then water could back up. Okay, so there is slope to it, slope alpha. So then if you keep the water table a foot away from the ground surface, then you have more that you can take advantage of. So you have a bigger head difference and you can get more flow through it. Okay, so here's the updated analysis where you have optimal width at any angle divided by, or any slope divided by the optimal width at zero slope. And then on this axis is the slope divided by, you can think of it as the slope of the water table. So it shows the calculations are okay because we start out as the slope of 0, we get a value of 1, which we should get here. And then the optimal width increases because you have more head difference. And then this dashed line here, beyond this, there's no optimum. So before this, wider is not necessarily better. There's an optimal width. Beyond this, you would do better just making it wider. Okay, well, that raises the question, where are we in Iowa? For those 6 sites, we'd be here, and this is a couple hours old. Here are the recalculations of that previous graph. You can see for 2 of the sites, BC1, BC2. BC2, the optimal width is now greater than the larger the current width when you account for the slope. BC1 is approximately optimal, which is interesting. The other ones don't change all that much. Okay, so that's a bonus that you get that wasn't in the paper. All right, so let's do details of the groundwater flow. That analysis assumes one-dimensional flow, and the design spreadsheet assumes one-dimensional flow. So Andrea set up a groundwater model, ModFlow 3D, and she wanted to test some of these assumptions. So up here we had the field, and we had flow from the field. Over there we have, to the right, we have the stream, and then the distribution pipe in this circle here shows she was looking at the paths of water leaving the pipe from different positions. So there's the top T, stream side S, bottom B, and field side F. And then here at position TF is about 10 o'clock, if you're old enough to remember analog clocks, which apparently my grad students are not. So, oh, and then one thing I want to say is that she took measurements of the denitrification rate from previous study, and then as she tracked the water, she could then calculate the nitrate removal along that path. Right. So here are the paths. Here's elevation Z, distance from a distribution pipe, X, 0 is the distribution pipe, that black circle. I should point over here. The stream is all the way on the right. You can see the water table, the blue line, that gets deflected upward by the water injected at the distribution pipe. The incoming groundwater, the streamlines get pushed down. And then I'll point out a couple of these paths. Path S goes almost directly from the distribution pipe to the stream. Path T goes up, stays high near the water table, where the organic carbon concentrations are high. Path TF goes up high, dives down low, and takes a long path. Path T is close to last for the travel time, smallest travel time, but it's so high up in the soil profile that it has the second largest nitrate removal. All right, so then she also accumulated all the travel times for 201 simulations and plotted a histogram of the travel time normalized by the one-dimensional estimate, the width divided by the average linear velocity. And so if the flow were truly 1D, everything would line up on this. Times that one-dimensional estimate, you get a very good estimate of the travel time. And that's very important for designing these buffers and calculating nitrate removal. Okay. And then the last piece here is on slope stability. This is Lulu Dickey's work. And so here's site BC2, which failed during our project period here. So if you've calculated, you've gone through all this trouble of calculating the optimal width and this big chunk falls away, then kind of bad situation. So we want to avoid this, obviously, right? That's why it was written into the code. So the code says the bank height is the key parameter, this bank height of 8 feet. Lulu is a recovering geotechnical engineer. And so she said, it's bank height, but it's more general than that. It's the site geometry, the bank height plus the distance to the top of the bank, the buffer width, and the angle of the slope. And so the higher the angle of the slope, the more unstable it will be. It also depends on soil properties. So the unit weight of the soil, the friction angle, and then soils in Iowa have significant clay content. So there's the cohesion. The higher the cohesion, the more stable the slope. So include that. And then we said that the water should matter. So seepage, we included parameters there. All right, this is what you're waiting for, I'm sure, is dimensional analysis. We defined a factor of safety. So that's the ratio of the forces resisting failure and the forces driving failure. So you would want the resisting forces to be greater than the driving forces. So nominally, you would say factor of safety of 1 or more, but you add to that, so 1.3. And then there's so many parameters. What we do in fluid mechanics is, I forced her to do this, is dimensional analysis and combine them. I won't go through a lot of the details, but I'll just tell you, the first one is the angle of repose. When you go to the beach and you're playing with the sand, which I still do at 55, and I pile it up and then it slumps to an angle, that's that right there. Then the effective cohesion from the clays, the effect of the seepage, and then a geometric parameter. So Lulu calculated the factor of safety for five of those sites, those buffer sites, with flow and without flow. Without is yellow and with is blue. And you could see in every case, the flow reduces the stability, the factor of safety, but it doesn't really change the conclusion about stability. So all these sites that were stable at first are still stable. I mean, this one's close, this one's marginal, IA1. And BC2, which is the one that failed, that one was going to fail anyway, with or without water. So, and then she ran 500 sets of these parameters to just explore the parameter space, essentially. So here's the factor of safety with flow against factor of safety without flow. And the green circles, the buffer was stable in both conditions. The red squares, it was unstable in both conditions. It's just the yellow ones, the yellow diamonds, that are where the flow in the buffer created, that was 3% of the conditions. So most of the time, the buffer doesn't create instability. Lulu took the results, used a generalized linear model to come up with an equation to predict the factor of safety, and it does very well. So if you have estimates of the soil properties and the site geometry and some of the seepage parameters, you could calculate the factor of safety. And so that would hopefully alleviate the need for an extensive geotechnical investigation and open up the number of sites to implement these buffers. So I'll conclude by summarizing these three pieces, that for saturated riparian buffers, wider is not necessarily better. The flow is one-dimensional, much of the buffer. That is helpful for design and for calculating nitrate removal. The buffer and I have one of them here. So more work on the nitrate loss rate, just in general, would be very helpful, and in particular for the optimal width would reduce the uncertainty. If we had I don't know if there's a good way to estimate that, very well. And I'm a fluids person, so I have ideas about the model of the flow in terms of this unsteadiness and modeling the control structure in more detail. So I'll thank you for your attention, and we can take questions.
Well, as another recovering geotechnical engineer, I want to look in more detail on that one, but I think we have time for questions for Tom and or Chris. So I'm gonna, if folks have questions, they can unmute themselves or raise their hand, and I'll call on you to ask the question.
I guess. Most of the streams you're looking at didn't have a spoil pile for drainage construction. How does the spoil pile impact siding potentially? Have you had conversations about how you can, frequently you're going to be outside that 12-inch foot?
I'll offer from a biogeochemical standpoint and then yield to Chris for any sort of stability issues or geotechnical issues. That has been a challenge because the conservation practice standard says you want to maintain that water within 1 foot of the soil surface at the box. And so if you think about that as you go towards the stream, if you have that spoil pile, almost by definition, you're going to be a couple 3 feet maybe below that surface. But in case in terms of performance, nitrate removal, I don't think that's going to make a difference at all because we've gone out there and taken cores of those down through the spoil pile. And sure, there's really low carbon there because that's that spoil coming up from the dredge and pretty heterogeneous. But as soon as you get down to the bottom of that, you're back to the A horizon. And so then you have that same soil horizon down there with still plenty of carbon. So I don't think that makes a difference for nitrate removal performance at all.
Right, from slope stability, if you pile up more soil right there at the bank, that will reduce the stability. That's not something we model. That would be an interesting case to do that. I would suspect that it wouldn't have a huge change of the factor of safety.
I know that some of these are going in on established buffer sites, and some of them are going on new buffer sites, so that the buffer vegetation is established at the same time as the drainage distribution networks put in. Would that have an impact on whether these sites have bank failure or not at EC2?
Can you repeat the question?
Can you say one more time, please?
Okay.
Yeah.
Some of these saturated buffers would be put in on new sites that don't have any established vegetation. Would that influence whether those sites fail or not?
Okay. So the effect of vegetation on the slope stability, right? So the calculations we didn't account for roots or anything that would increase the stability. So any vegetation would I would think, I'm not a geotech at all, so I would think that would increase the stability over what we modeled. Yeah. I have a question for Tom.
No,
Tom had
is that fair?
You had future work on the slides you sent me, and then I might have misled you into thinking I was going to put all that at the end of the talk, and I didn't do that. So do you have any things you want to?
No, actually, what Malcolm was back there putting up the sign that I was running out of time, so that was one that I said, okay, I'm not going to include that. Yeah, and I thank you for that. So from a research perspective, some of the things we need to look at, I think, is still this tie between soil carbon and soil and the lability of that carbon on buffer performance and other adaptive factors, particularly as we get off of most of our history of monitoring is on soils that are in the Des Moines lobe. And as we get over into the Iowa erosion surface and maybe into other loess-based soils, I think the difference in those soil adaptive factors and some of those carbon lability and other things are going to be important, and we need to look at those and push the envelope a little bit on some of those sites. So that's one of the biogeochemical ones. And then from a more practical perspective, we need to take that information and you know, the nice thing about this is that we're up to maybe 200 saturated buffers, and they're really being heavily promoted. We need to do our best job as the researchers of making sure that the most up-to-date information gets put into those site selection and site design criteria, and that also gets put into the models that are being used to assess performance.
I should know this, but what other states are also putting in saturated buffers? Is the performance in those other locations been similar to what you've documented?
The only other papers that are out there that are documenting performance, Keith Schilling has one here in Iowa that had some similar performance, and then there's the work that's being done by Laura Christensen and gang over in University of Illinois, and it's been pretty consistent in terms of but again, it's all percent removal. It's all percent removal, and we're all advocating to try to think about kilograms in.
Kind of a silly question, but has there been any work on phosphorus? Do you expect that you might be storing some soluble phosphorus and bring it through the soil?
Yeah, so the question was, has there been any better work on phosphorus? Yes, not enough, and we're continuing to work on it. So in general, because when we look at these as nitrate removal, we have denitrification going for us. It's the permanent loss to the atmosphere. With phosphorus, there is no gaseous phase of phosphorus that's of any consequence. And so really we're really just going to be retaining on the binding sites within the soil. So we are careful in advocating for nutrient removal wetlands or bioreactors or saturated buffers that rely on denitrification as phosphorus removal. We have 1 year of data where we've looked at phosphorus. It's sort of ambiguous, doesn't really tell us much. But it's not a question that's a totally unsatisfactory answer. And we recognize that's a totally unsatisfactory answer. So just last year, we've started to increase the monitoring. Gabe Johnson has put in monitors at 2 sites, Bear Creek 2 and another site that has a lot of flow, and we'll continue to monitor that. One of the other things that's a little bit trickier to measure with phosphorus is that's so episodic. And so rather than just going out there once a week and measuring a nitrate concentration from the box, we need to have the automated samplers out there to catch that flow.
Any questions online? Don't see any. All right. With that, I want to thank Tom and Chris with a INRC mug.
Check it out.
Thank you for your participation, and be sure to tune in March 8th. We're going to talk about bioreactors, ditches and oxbows with Michelle Sapir and Keith Schilling. So please tune in then. I hope everybody has a good rest of your day. Thanks for attending.